Okay, good morning, everyone. Oh, okay, thanks. Appreciate it. All right, let's see. Mic testing, check one, check two. All right, works. Okay, any questions about any of the material we have covered so far? Okay, all right, and everybody got notification or received the notification about quiz 0? Okay, so I'm again confirming. I know that when I post an announcement, students receive an email. I just wanted to confirm that the notification does arrive. If it does not, then you can go into your Canvas app and change those notifications settings. Okay, so let's pick up where we stopped, which is right here. So PN junction diode, we went over a little bit of the construction, semiconductor physics, and then covered how a p-type and a n-type semiconductor can be fabricated in close proximity, and it creates a solid state version of the vacuum tube diode. Okay, so similar to the vacuum tube diode, a solid state or a semiconductor PN junction diode is a one-way device, and that one-way notification is illustrated by this arrowhead pointing towards the direction of the current. The names of the terminals carried over from the vacuum tubes. So the positive terminal, the p-type terminal, is still labeled as anode, noted by uppercase A, and then the negative or the n-type material is noted with a cathode, uppercase K. All right. And in real life, when you have a diode, there is usually a band marking the cathode. Okay, the band illustrates or notes the cathode in that device. So we talked a bit about external biasing, external source. So PN junction diode by itself is, it has some properties. We are not here to discuss those properties because, even in E major classes, we discuss those properties just a little bit. Non-E major class, we just talk a little bit about the movement of electrons and holes, and then we get into the circuits. So when you connect a positive terminal of the battery to the p-type material and the negative to the n-type material, we say that the diode is forward bias. Electrons and holes cross over the depletion region in the middle, and then we have current flow through the device. One important point I'd like to make is this. The current flow is due to both holes and electrons, okay, or electrons and holes, however we wish to state. So it's due to electrons and holes. So when electrons and holes move in a circuit, they are carrying charge, they transfer energy, they're transferring electrical energy from one point to another point. So they are known as charge carriers because they carry charge. In a p-type material, you have an excess of holes. Right? In a p-type material, you have an excess of holes. So the term we use is majority and minority charge carriers. So in a p-type material, the majority are holes and minority are electrons. In an n-type material, it's the exact opposite. The majority carriers are electrons and minority carriers are holes. So electrons and holes, okay? because the current is due to two different types of carriers, these devices are also known as bipolar devices. For diodes, we do not use, in general, we do not use bipolar device, but the technical term for a bipolar electronic device or bipolar semiconductor device comes from the fact that the the current in this device is due to both electrons as well as holes. The reason I'm pointing it out now is because the next device after this that we look at is the transistor. And the technical name of the transistor is BJT, bipolar junction transistor. The bipolar stands for both electrons and holes. There are two junctions in there instead of one. And then, of course, it transfers resistance. That's where the name comes from. So this is for both diodes and transistors. Anyway, coming back to our circuit. When we say that we have connected the positive end of a voltage source to the p-type material and the negative terminal to the n-type material, it does not always have to be 0 and 5 or 0 and some plus voltage. In reality, it's simply noting the potential difference between the two terminals. So if you have, and I believe I mentioned this on Monday also, if you have a diode and one end is at, let's say, plus 10 volts, the other end is at 5 volts, meaning the anode is higher than the cathode, that still means that the diode is forward biased, because the electric potential across the anode and the cathode would translate to plus 5 volts to 0 volts. Let me scroll. Let's take a pause while you think over what this means, and let me know if you have any questions. Any questions?
Yeah, I have a question.
Yes, go ahead.
I might have missed this, but can you just explain quickly what holes are again?
Holes is basically the absence of an electron. So when electron moves, so we are talking about the atomic structure in a material, and when a electron moves from the valence band to the conduction band, meaning it is now available to conduct electricity, then it leaves behind an empty spot in its place. That empty spot results in a positively charged ion, and we name that empty spot as a hole. And for purposes of analysis, we treat it as a particle that is exactly the same as an electron, but has a opposite charge.
I'm guessing we're going to be going over how to diodes.
Yes. Yeah. So the questions being asked is about how we're going to use diodes in the circuit. Yeah. All right. So from forward bias, we then go to reverse bias, where the n-type material is now at a higher potential than the p-type material, or the positive end is connected to the n-type material. And what that does is, at the interface of the junction, meaning at the interface of P and N, the depletion region expands. And so let's say this was the original depletion region or original width, and then it expands from that point on. It's because you have a n-type material and a p-type, means you have electrons here and you're applying a positive charge at that terminal. So it attracts the electrons, and at this side, you're applying a negative charge, and so it attracts the positively charged holes. And so it expands the junction, meaning there is no movement of the charge carriers across the junction. There's no current flowing because if charge carriers are not flowing through the junction, there's no current. And so in reverse bias, there is very minimal current flow. Okay, very minimal current flow. And again, when we state here p-type material is negative, it does not mean it's negative or positive, but it's negative and positive with relation to the other junction, meaning the p and n-type material. The n-type material would be higher than the p-type material. And that's what the positive and negative indicate. So the positive and negative here simply is a relation to the other end of that junction diode. Let's take 10-second pause. Think over that. Let me know if you have questions. Any questions? Yes. So the junction, so the question being asked is, what does minimal current mean? Okay, the answer is that when you have forward bias, energy from the external source is now imparted to the holes and the electrons. So they have sufficient energy, they acquire sufficient energy that they can now move. And when they move, well, when charge, they are carrying charge. So when those charge carriers move, it results in current flow. For reverse bias, the exact opposite happens. The depletion region means there's like a border between the two p and n-type material that expands. And because it expands, there is very minimal movement of charge carriers. Some electrons and some holes will still drift through in response to the electric field. But for the most part, because the region is expanded so much, there's going to be very, very little movement. Because the region is expanding, no matter how much energy you provide, it needs to cross over that barrier, which just physically is not possible. Does that make sense? Okay. Anyway, the end result is that the diode, similar to the vacuum tube version, conducts electricity or conducts current only in one direction. So it's like a one-way device. Okay, it's a one-way device. And we use the fluid flow analogy that I like to use in 201 also. You have a pipe. The pipe is, it should be like that. The pipe is the electrical conductor, or analogous to an electrical conductor. And the fluid flowing inside it can be termed as electrons, or in this case, because it's electrons and holes, we can simply say it's the current. Yes. Yes. Yeah. Electrons will be flowing opposite. So again, at this, I always like to point out to students, we do not, this is a specialization within electrical engineering itself. Okay. It's even EE students do not learn about the physics of this until they go to like a 500 level class. So 201 is like, let's see, the classes that EE take is 113, 211, 212. 321, the classes that EE students take are 306, 307, 308, 300 level classes. Even in those classes, students learn maybe one chapter about the semiconductor physics, and then we move on to the circuits. If you do want to learn about the semiconductor physics of this, there's an entire separate class, 524, solid state electronics, senior level, graduate level class. So there's a ton of information. There are lots of books about like, PN junction diodes, solid state mechanics, semiconductor physics. It's a whole different device. So what I like to tell students is, it's great that you would want to understand everything, but the primary objective of this course would be how to use these devices to create a circuit, and how would you analyze a circuit as a non-EE engineer. If you do have questions about semiconductor physics, I'd be more than happy to answer outside of class. Okay. Anyway, so as I was saying, coming back to our topic of discussion, diode is a one-way device. You can use it as a one-way valve. Current flows in one direction, fluid is flowing in one direction, automatically the valve opens up. If you try to go in the opposite direction, valve closes, there's no more current flow. Okay, there's no more current flow. So again, I always like to use the fluid flow analogy. It makes a lot of sense. Hang up the electrical with the mechanical example. Okay. So let's look at the diode VI or IV characteristic. The VI characteristic stands for voltage current relationship. Okay, characteristic basically means it's a graphical illustration of two or more quantities. So in electrical engineering, we use this word to describe devices, components, circuits. We use it for lots of things. Basically, it means you are describing a system graphically. So the diode IV or VI characteristic both mean the same thing. VI or IV simply represents the voltage and current, or current and voltage. So this is the positive voltage. This is the negative voltage, negative current, positive current. First quadrant, positive voltage results in a positive current. Now, these are exaggerated. Okay, they are not on the same scale. In the forward bias, if I was to expand the curve on the x-axis, and let's say this is 0 and this is 1 volt, then a diode characteristic would look something like this. Because of the depletion region, until we get to, and the angle also is exaggerated a little bit. And we'd say approximately here, which is about 0.6 to 0.7 volts. That's where the standard depletion region is overcome. Remember, when we bring the P and N junction together, there is a depletion region that forms at the junction. That depletion region is so called because it is depleted of charge carriers. Because they're in close contact, electrons from the N side and holes from the N side will recombine. If they recombine, it means electron jumps into the empty spot, thus removing one electron from the N side and one electron and one hole from the P-type material. So you have one less negative charge and one less positive charge. And when that happens, charge is gone. It's a depletion region. And it's basically, let's say up to here is your depletion region. You apply an external bias to it. When you apply external bias, meaning external voltage, you have an external energy that is now being imparted to the electrons in the holes. And because of that energy, they start moving across the depletion region. And at some point, all the carriers will acquire enough energy to cross over the depletion region. And that voltage is right here. It is known as the diode forward bias voltage, VD. Actually, you know what? So forward bias voltage, it is also known as the knee voltage because of the shape of a knee. And this value, 0.6 to 0.7 volts, is inherent to the material. So for silicon, this diode voltage is 0.6 to 0.7 volts. And of course, it fluctuates with respect to temperature, but is in the range of 0.6 to 0.7. If we make it out of germanium, it is 0.2 to 0.3 volts. Yes. Okay, so the question being asked is, once we apply an external voltage, do the electrons and holes acquire enough energy to actually move across the junction and recombine? Is that the question? They would kind of leave the diode in that sense. So if you're talking about, but then we get into a little bit of semiconductor physics. Externally, it'll be made out of some sort of metal. Metals have electrons for conduction, but not holes. So the holes and electrons would actually stay inside the diode. What is actually moving is the energy. Charge is moving across the junction. So there is electric current that is flowing, but whenever we say electric current is flowing, it means that there are charge carriers that are actually flowing through the junction. And so they transfer the energy from across the junction and into the terminals, but they would not specifically leave the terminal as such. Talking about physically leaving the terminal, right? Yeah, physically, no. No, energy is being transferred. The energy would go, the charge would go, but not the actual electrons or holes themselves. If students have taken, I want to say, any topic in analytical chemistry, electrochemistry perhaps, you have a liquid that can conduct, will have some ions, and you have a metal conductor inside that liquid. What happens at the interface? You have metal, that means there are electrons to conduct charge, but when it gets to the interface of the liquid and the metal, the actual metals will not travel into the liquid. Well, there are many other considerations there too. Unless you apply a whole higher voltage or energy, which will then start corrosion. But if you have ever taken a class or a topic in electrochemistry, it's kind of like similar to that. So until a certain point, it's not going to leave the actual device. Does that kind of answer your question? Okay. All right, so that's the forward bias region. What happens when you reverse bias it? Well, when you reverse bias this, meaning you're applying a high voltage in the reverse direction, the N-type material is at a higher potential than the P-type material. There is no current flow for a long time, except for a minimal flow for a long time. And so the depletion region expands, right? The depletion region expands. And this value is, let's see, probably like greater than 70, 80, or even 100 volts. So the depletion region keeps expanding until a point arrives where the external energy that is applied by that voltage source impart so much energy to the charge carriers that they then cross the junction barrier. So the depletion region keeps expanding, but at some point there's a breakdown. So there is a breakdown and there's a huge influx of electrons and holes crossing over the junction all at once. And so that is shown by this acid drop on the left side. So this is known as a breakdown of the junction. Breakdown of the junction. So again, depletion region keeps expanding, but there's so much energy being provided from the external source that even though the depletion region is expanded, there is a huge amount of charge carriers. Now they acquire so much energy that they cross the junction and current starts flowing, but now it's in the opposite direction, not in the same direction. Again, your reverse bias. So you're applying negative voltage, results in negative current flow. This breakdown, just to get a little bit into semiconductor physics, is due to two phenomena that take place. And the first one is Zener breakdown, and the other one is known as an avalanche breakdown. So there are two phenomena that take place when the junction breaks down. The first one is known as the Zener. The second one is known as avalanche. Zener happens due to high impurity doping. And I think let's not get into more into impurity doping. And this is about low or standard impurity doping. Doping is basically the process of introducing impurities into a semiconductor material. High and low refers to the amount of material that you introduce into the semiconductor. So high impurity doping means you have a silicon material or a germanium material, and you flood the surface of the silicon material with a huge amount of impurity. Phosphorus, boron, doesn't really matter. Whatever that impurity material is, it's known as a dopant. The process of introducing the impurity in there is known as doping. So high doping means a very high dose of phosphorus, boron, arsenic, gallium into the semiconductor material. Low doping means a low amount, and low and high are relative. This is still in 10 raised to 17, 10 raised to 16 atoms. Zener breakdown typically occurs for less than 6 volts. Avalanche is it's greater than 6 volts. But once it breaks down, the voltage across that junction remains near constant, meaning you can increase the voltage that you're applying to this diode, but the voltage across the diode will remain constant. This is very important because one of the devices that we learn about is the Zener diode. The Zener diode is specifically engineered and fabricated to hold a voltage across its terminals constant. Okay, it holds the voltage across its terminals constant. Yes.
Can you take that concept to the extreme? So far?
What would you refer to as extreme? There are high power devices. So the question being asked is, can we have very high voltage devices? The answer is technically yes. I personally have not used or come across any of those, but I would assume that electric power stations, which deal with thousands of volts, would have some devices like that. Simplistically saying, like, if you want higher voltage and higher current and higher power capable devices, you would simply increase the size of the device. There's of course physical limitations, but technically it would be possible. One important fact is that diodes, which are engineered to work in the reverse bias, are collectively known as Zener diodes. So the mechanism could be Zener or avalanche, but they're collectively referred to as Zener diodes. So one question might come up is like, if you have a 9-volt Zener diode, but it would probably be avalanche mechanism, why would we call it Zener diode? But that's just industry standard. Okay. And I have to thank my colleague, Professor Chuck Bland, for many of these images. The fire here is basically there's always a danger that you might inadvertently end up damaging your diodes. So diodes will come with a rating or a peak inverse voltage. Even the cheapest of diodes that we use has a PIV of like 50 or 60 volts. Okay, so if you use a diode at like 4 or 5 volts, you can still apply 50, 60 volts in the opposite direction and it'll still work fine. There are diodes specifically from the 1N4000 series, goes all the way up to 1N4007, can take up to 400 volts in the reverse bias. It's just the manufacturing. Okay, now we get the actual circuit analysis. And I'm going to ask students if this looks familiar. What does it remind you of? Yes, the equivalent circuit. Absolutely. It's a Thevenin equivalent circuit. Remember, I said you're not going to get rid of Thevenin and Norton that quickly. So we have diodes. We connect diodes. Diodes could be part of a large circuit, a huge circuit. The way we would analyze it is we would take all the linear components in the circuit and we would reduce it to its equivalent circuit, equivalent Thevenin equivalent circuit. Whether it's Thevenin or Norton depends on the application. For the most part, in this class, we'll deal with the Thevenin equivalent circuits. So again, we don't have to do any analysis right now. This is for explanation purposes. It's simply saying there is a large circuit, and that large circuit has a single diode connected to it, and it has a voltage, it has a resistance, and we don't really care what that voltage is comprised of. We don't really care what that resistance is comprised of. So we'll deal with a circuit. The important point is we separate out the linear components of the circuit and we keep the nonlinear diode on one side. Okay. So if this was, let's say, instead of a diode, we had another resistor in there, then we know that we can find the voltage and current across that resistor through the any analytical method that we've learned, KVL, KCL, Ohm's law, right? But now we have a nonlinear device in there. So what do we do? Well, there are many techniques, but one of the most important is known as a load line analysis. Load line analysis. So if you look at this circuit, what do we see? We have a voltage source, we have a resistor R, and we have a diode. The notation for the diode is an uppercase D, and the voltage and current are in lowercase. So the diode voltage, VD, refers to the voltage across the diode with the positive at the anode and the negative at the cathode. Okay. And again, think of the concepts that we learned in 201. Positive, negative simply means which terminal of that element is higher than the other. Okay. If VD is plus 5 volts, it means anode is higher than the cathode of the diode by 5 volts. If VD is minus 6 volts, that means the anode is 6 volts lower than the cathode. That's all it means. Okay. And then similarly, the current flowing through the diode is labeled as ID. ID. So to analyze such a circuit, we apply KVL. What do we get? Voltage source VSS on one side. Then we have, so this would be minus VSS plus ID times R plus VD equals to 0. This is just my way or my style of writing a KVL. You would have your own preferred method. You can use that. That is fine. But obviously, the equation that we obtain is VSS times RID or IDRD plus VD, which makes sense. You have one energy source in there, VSS, and you have two passive two components that act as a load. You have the resistor, you have the diode. So the voltages across those two components should add up to your total source voltage. So VSS is equal to IDR times VD. Now, take 10 seconds, look at this graph, think over that before I begin an explanation. What do we see? Now, one of the answers is voltage limit, yes. Anyone else? First day of, or first class of 201. I don't know if your professors might have stated this or not, but what is circuit analysis? What is the purpose of circuit analysis? What does it mean? Anyone? Circuit analysis is the process of determining the values of the unknown quantities in a circuit. Unknown quantities could be voltage, current, power, energy, so on and so forth. But primarily, unknown voltages and unknown currents, right? Here, we have two unknowns, the diode voltage VD and the diode current ID. If you have two unknowns, if you have two unknown variables, how many equations do you need to solve for those two unknown variables? Two, right? But we don't have two equations. We only have one equation. So this illustration, this graphical illustration is displaying a solution of this equation right there. Okay, it's displaying a solution of that equation. That's what it is doing. So we have the diode characteristic, which is pretty standard, right? And then we create a line, a straight line, and we call that as the load line. And so this analysis is termed as a load line analysis. This is a very important concept in electrical engineering. This is used throughout. An EE student uses this throughout their entire career as an electrical engineer. Load line analysis, we're going to use it for diodes, Zener diodes, transistors, pretty much any circuit that we will look at in the. And so we have the diode characteristic, we have the load line. The intersection point is termed as the operating point. So the intersection point right here is termed as the operating point. It is also known as a Q point. The operating point is also known as the Q point. And this Q stands for quiescent. Let me scroll up. Q stands for quiescent, because it can move depending on the value of R and VSS. So let's take 10-second pause, think over that, and let me know if you have any questions. Yes. I will explain that, yes. Any other questions? Okay, so the question being asked was, well, basically it was about the next topic, not topic, but the next explanation I was going to give is how and why do we use this particular line, right? How and why do we use this? Well, we only have one equation. So if you want to plot, we need at least 2 points. So the easiest way to plot this kind of line is basically by substituting. So substitute ID and VD equal to 0. And then we obtain values for VD and ID respectively. If ID is equal to 0, then the diode voltage VD is simply equal to VSS, right? And that is basically this point right here. If VD is equal to 0, then ID is VSS divided by R, which is this point right here. So this is actually, I already have ID is equal to 0, and here VD is equal to 0. We obtain 2 points. We join those 2 points, we obtain a line. The intersection point is the operating point of the diode, or the operating point of the circuit, not of the diode, of the circuit, which is also known as the Q point or the quiescent point. Quiescent because it can move depending on the values of R and VSS. If you increase VSS, if VSS increases, then this line moves up. The operating point is going to move up. If you decrease it, it's going to move down. So this is if VSS increases, this is if VSS decreases. Make sense? Right? If VSS is increased, meaning if this was for 5 volts and now you increase it to 6, 7, 8, 9, 10 volts, the line starts moving in this direction, meaning it's going to go like this. So then your Q point increases. If VSS decreases, your Q point or operating point decreases. And same thing happens if R increases or decreases, right? Actually, the inverse happens because R is in the denominator. So if R increases, then the point will actually go down. If it decreases, then the point will go up. And that is basically load line analysis. Okay, for any circuit, we would take this is of course a Thevenin representative. So you have one voltage source, one resistance, and one diode. We can use load line analysis to find the diode voltage and the diode current. All right, any questions before I move to an example? So one thing about this is also that you have a device. The device can be used for a variety of functions, right? But the device by itself is not going to do any good unless you apply an external energy source to it. So you have an external circuit that is applying or supplying energy to that diode. But because it is the one that is supplying the energy, it also imposes restrictions on the diode at the same time. Make sense? And so that circuit restriction is also known as the biasing circuit. Bias simply means how you're going to use that device, whether it's a diode or a transistor. That external circuit, which the engineers would design that external circuit depending on the application. That external circuit imposes restrictions on the operation of the device, and it's known as the biasing circuit. Biasing circuit. So let's look at 2 examples, and then we'll take a short break. So example 1 and example 2, we are provided with the external energy source, and the value of the resistance, and you're asked to find VD and ID. Okay, and in and in both cases, what we're going to do is we're going to use or assume that the diode is 0.6 volts, silicon diode. Okay, it doesn't make a difference here for our analysis, but that's typically what we're going to look at throughout this chapter. So, for example 1, we have VD is equal to 0 volts. We find from the equation VSS is ID times R plus VD. Actually, so when we plug in VD is equal to 0, we get ID is equal to VSS over R, which means it's 2 over 1000. So 2 milliamps. When ID is equal to 0, VD is straightforward equal to VSS, which is 2 volts. 2 volts. So write it down. Let me know if you have any questions. Sorry, this monitor doesn't go down. This is as far as it goes down. Make sense? Any questions? And then for example 2, and I'll plot this on the same graph down on the left. But for example 2, what do we have? When VD is equal to 0, we get ID. And again, this is VSS divided by R. VSS is 10 divided by 10,000. And so this gives me 1 milliamp. And for the second part, ID is 0. But if ID is 0, what do I get? VD is VSS, which is 10 volts. So if I want to plot everything on the same graph, let's say I'm an engineer, I'm trying to design a circuit for a specific purpose, then I know what my output should be, right? Engineering is always, in some ways, it's always reverse engineering. You know what the output is. Now you have to devise a system that would fit that output, right? So here I have a device, I have a diode, I know the specifications of the diode. Now I need to figure out the voltage that I need to apply and the resistance that would work. So in both cases, the diode is the same. I have VSS 2 volts, VSS 10 volts. So the 2 voltage limits, and then R is 1000 and 10,000. So if I wish to plot both on the same graph or the same chart, then I need to have at least 0 to 10 volts, like a line going from 0 to 10 volts. So, and if I don't want to do that, then I can just find another plot on the line. So let's see. That should be good. So this is voltage V or VD. And this is current I, ID. Oh, by the way, typically it's always VI characteristic. So voltage is always on the x-axis and current is always on the y-axis. Okay, unless there's a specific need to display it in a different way, voltage is always on the x-axis and current is always on the y-axis. Okay, so if I was to plot this, I would need to go at least from 0 to, let's say, 10, right? And of course, this is completely approximate. So if that's 2 or 2 milliamps, this would be 1 milliamp here. And then let's see, And maybe 5 is here. And then 1, 2, 3. Oh, that's not even close. It's 2.5. Maybe 2 is here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so if it's 1 and 10, and then 2 and 2, oh, right there. And obviously, as I said, this is not to scale. So this is example 1. Oh, sorry, that's 2. And this is example 1. And then, of course, you would already know the diode characteristic or the diode specification. Sorry, not characteristic, but specifications. If you're using germanium diode, it'd be somewhere between 0.2 and 0.3. If you're using a silicon diode, it'd be 0.6 to 0.7. So depending on the diode that you're using, you could draw out something like this. Oh, not like that. And then if it's a silicon diode, maybe a line right here. Something like this. So now you would know what your diode voltage would be depending on what system, I mean, what power supply or what value resistor you would use. So you'd have multiple iterations. Previously, obviously, before the age of computers, we would plot this manually. Now you have powerful computers. Actually, you don't even need a powerful computer. You only need some software, whether online or on your desktops, laptops, and you can plot this out and you can have hundreds of results within a few seconds. Yes. Okay, so a question being asked is what conclusions can we draw from this? Well, there's no conclusion as such. This is the process of determining the operating point of a diode. But I guess if I understand your question correctly is, why would we need a circuit like this? Well, not circuit, but let me phrase this correctly. What is the application of this, right? That would be the question. Okay, so the application could be anything. In real life, I think one of the most common applications for a diode is in a digital thermometer. In a digital thermometer, and the reason is because the diode's characteristic changes very linearly with change in temperature. So there is a very simple circuit comprising of 2 diodes and 2 sources, and it just compares the 2 points. So depending on the temperature, the diode voltage or current shifts up or down. So if you already know this, which of course it comes from the manufacturer of the diode, that this is known from the spec sheet. And then let's say you're trying to build a digital thermometer, for instance, as an application. Then you would know and depending on the space that you have available, you would know whether you can insert like 1 small battery in there, 2 batteries, 3 batteries perhaps, depending on how big or small you're making the thermometer. And you would know whether you're using a 1.5 volt battery or a 3.6 volt button cell, you know, those coin cells. So then you would know that voltage. And then you can figure out, depending on your application again, where you would like the diode to operate. So load line analysis, again, is the application of this method is to determine the operating point of the diode. Let's say you apply 1 volt to it instead of 3.6 or 1.5. You apply 1 volt to it and you perform an analysis and you figure out the diode is somewhere over there, very low end. We don't want it there. We want it to be in the linear space, right? We want the diode to turn on. We don't want it somewhere down here. So not in this space and not in this space. We want it to be in the linear space of operation, where the diode current or diode voltage would change linearly. Make sense? So depending on the value of the resistor, the diode could be operating anywhere along that line. And so that's how we would use this load line analysis to determine that. That's where the purpose would be. Sure. So the question being asked is, if we look at the load line and we find that it's not actually intersecting our diode characteristic, then this is a good way to determine whether it does or not. Yes. For the most part, actually, I drew this incorrectly, and I just realized it now. Because it's 0.2 and 0.6 volts. It's not 2 and 6 volts. So this is supposed to be 0.2 and 0.6, not 2. I'll leave the error in there. And now I see why it's confusing. So you'd have, question being asked is, if you have 2 or more diodes in the same characteristic. So wait, let me, you know what, let me go ahead and fix this. So you're saying if you have a plot like this, oh, you're talking about this point right here. But that doesn't matter. That just depends on the application. Yeah. Okay. Okay, so it's 11:08. Let's take a short break, maybe 5 minutes, and we'll pick up again at 11:13. And I'm still here if students have any questions. So you were specifically